Hello everyone, I am Nazmul Ahsan and today I am going to discuss my paper High Frequency Instruments and Identification Robust Inference for Stochastic Volatility Models. Before I begin my talk, I would like to thank the organizers for this virtual conference. This is the outline of my talk, and this paper is about time-varying volatility. Dynamic volatility has consequences for many problems of financial decision: risk management, portfolio allocation, asset pricing, and other areas like hedging and trading. Two main classes, these are the parametric classes of models, have been proposed for dynamic volatility. These include gauge type models by Angle and stochastic volatility models of Taylor. And between these two models, volatility is modeled as a latent stochastic process in stochastic volatility models, and which is more appealing compared to the gauge type models for several reasons. This includes it's a discrete version of continuous time analogs that people used in option pricing literature. Also, empirical evidence suggests that SB models are more robust to model misspecification. These models also provide more accurate forecast of volatility, and the statistical properties of SB models are relatively easy to derive. In this paper, we view SB model as dynamic error invariable models. Basically, in a typical stochastic volatility model, volatility is modeled as a latent stochastic process. Residual return ST follows this sort of heteroscedastic form, and log variance follows an AR1 process, and this process is a latent process. If you set this 3, then you can rewrite equation 1 as this, which you can easily see that this is a dynamic error invariable model. As a result, in this paper, we consider the instrumental variable methods to make a statistical inference on this type of SB models. And for instrumental variable methods, we need valid instruments for the latent volatility. And we also extend this model by incorporating an instrument equation such that we introduce a new class of discrete time SB models which can use many measurements of latent volatility. So in this paper, the instrument equation 5 can relate many realized volatility measures to the latent log volatility. And if you look at this model, this proposed model 3-4 corresponds to any standard SB model. In this framework, we use RV measures as instrument for the latent volatility, in contrast with the recent studies where realized volatility has been incorporated in traditional volatility models, GARCH or SB, by adding a measurement equation that connects the low frequency volatility to the realized volatility. In this proposed framework, we consider the problem of testing hypothesis and building confidence sets for the volatility persistence parameter phi. This parameter plays a key role in many areas of financial economics. For example, asset allocation. Asset pricing theories have shown that the persistence in risk premium can be reflected by this parameter. When there is a high persistence in volatility, a rational investor should constantly and permanently change the weighting of assets whenever a volatility shock arrives. Let's look at the whole process here. If there is a new information arrives and it produces a volatility shock, then the current level of volatility goes up. And when phi is high, it means that volatility shock persists, so the next period volatility also goes up. And when volatility goes up, rational investors want additional return for these assets. So they want additional return, which is the risk premium. So risk premium goes up, and this requires immediate rebalancing of these assets because investors are risk averse and they will make decision based on their degrees of risk aversion, buy or sell. So the trading frequency of these assets increases. So phi captures a very important feature of these volatility models. This also has implication in risk management and option pricing or asset pricing, because a confidence set of phi determines the conditional volatility forecast interval given the current level of volatility, which is important in many areas of financial research. And given phi determines the conditional volatility forecast interval, in turn, it also produces a prediction interval of returns through projection technique. And this is the risk-return trade-off in financial assets. So the first point is this is the accurate estimation of the tails of return distribution are of particular importance for risk management tools. This is in the context of value at risk and expected shortfall risk management. The volatility forecast interval is also important for option pricing, and the accurate confidence interval estimation of volatility has consequences for the forecast of the conditional mean. So this is the prediction interval of returns. So the researcher may want to test for a general restriction on phi or for non-stationary of the volatility process by testing for a unit root in the log-squared low-frequency returns in a model setup which utilize high-frequency information. Or, on the other hand, the researcher may want to build a valid confidence set of phi that can be used to determine the volatility forecast interval and or the distribution of the volatility forecasts in the proposed model setup. So we consider testing volatility persistence parameter, and we also consider building a valid confidence set for this parameter. Previous attempts on hypothesis testing for the volatility persistence parameter are limited, and this includes Harvey, Wright, and these are the other two studies. Harvey suggested a classical unit root test in a quasi-maximum likelihood setup which suffers from large size distortion, whereas Wright proposed to use the unit root test of Paranon NG, but this test procedure is based on large sample approximation and may not reliable in finite samples and different parameter settings. Actually, these procedures requires a larger samples. Dufour and Valerie and Ahsan and Dufour developed both exact and asymptotic tests for no persistence or no clustering hypothesis, and these are largely based on stationarity and normality assumptions, and applying these procedures in real data may be problematic since the latent log volatility process can be highly persistent. All these previous studies did not exploit high-frequency information. It means that there is no additional measurements for volatility. Let's look at a small simulation. What happened when you test volatility persistence parameter? This is the size of asymptotic t-type test. For the null, phi is equal to phi naught. The nominal level is 5% and number of replication is 10,000. And if you see that when phi goes to 1, it's close to unit root, then the size distortion goes up. So this test fails to control the type 1 error. Even this remains even in the larger sample. So when phi tends to 1, the asymptotic approximation is very unreliable in finite samples and leads to large size distortion. This assertion is also supported by Harvey and Wright. In this paper, let's talk about our contribution. In this paper, we propose inference methods which are robust to dynamics, means non-stationarity. We proposed 4 different type of testing procedure: Anderson-Rubin type test, dynamic version of split sample type test of Dufour and Jasiak, and point optimal version of this test. Point optimal tests we proposed gain power by exploiting the differences in the error covariance matrices under the null and the alternative. The proposed inference procedures are also robust to weak instruments because the potential high-frequency instruments may be weak due to the discretization error or market microstructure noise. For distributional theory, we considered 3 different sets of assumptions. And our simulation results show that the proposed tests outperform the usual asymptotic tests in terms of level control and exhibit excellent power. These findings hold for several empirically motivated misspecified model setup. Due to time constraint, I'm going to talk about some simulation results and some highlights related to to our empirical findings. And for the more technical analysis, please look at the paper which is available in my website. This is a simulation results of the size comparison of tests where null hypothesis is phi LF. LF is the low frequency phi equals to some restriction phi naught. And we consider high frequency instrument. In this case, this is the realized volatility. And the number of instruments, it's an IV type method. We consider one instrument and the nominal level is 5% and the number of replication is 10,000. There is a nuisance parameter which we replace by a point estimate. So this is the frequency 1 minute and 5 minute. This is the phi LF, and you can see that this is our four proposed testing procedure, and this test procedures control the level, and we have the similar results also with higher or larger samples. Let's look at the power, and this is the power against the null phi LF low frequency phi equals to 0, and you can see that when you go further away from the null, the power goes up, and this is for all these tests. And if you increase the length of the simulated samples, then the power also goes up. So this is some simulation results. So the proposed test procedures are robust to the dynamics. You can see that, and this controls the level and also exhibit excellent power. Now let's talk about the empirical results. We apply our proposed inference methods to IBM's price and option data, and 5 years data, and this is between 2009 and to 2013 and 1258 trading days. The low frequency daily prices are obtained from CRSP database. IBM tick price data is the high frequency data is taken from trade and quote, and option prices are taken from the option matrix database. Using this data, we construct 175 different instruments which is spanning in 22 classes, and we analyze their ability to describe the low frequency volatility. And this is the highlights of our empirical results. The superior instrument set we find mostly consists of 5-minute high-frequency realized measures, and these IVs produce confidence sets where the volatility persistence parameter lies roughly between 0.85 to 1. These findings prove that high-frequency realized volatility does provide an additional gain in predicting the low-frequency volatility. The volatility process is highly persistent, close to unit root, consistent with the empirical literature. These confidence sets include phi is equals to 1, implying that these tests are also robust to non-stationarity. The average implied volatility that extracts from IBM American call option is also informative regarding the low-frequency volatility. This finding is in line with the Christensen and Provala, who finds that implied volatility has large explanatory power regarding past volatility. We find that RVs with higher frequency produce a wider confidence intervals compared to RVs with slightly lower frequency, showing that these confidence intervals adjust to absorb market microstructure noise or discretization error. When we consider irrelevant or weak IVs, in our case it's jumps and sign jumps, we find that these are the weak IVs. The proposed test produces unbounded confidence intervals. Although jumps contain little information content regarding the low frequency volatility, we also find that there may be a nonlinear relationship between jumps and the low frequency volatility. Let's talk about a little bit, let's summarize this paper. We introduced a novel class of stochastic volatility models which utilize high frequency information and accommodate non-stationary volatility, various distribution assumptions, and exogenous regressors in the latent volatility. We propose inference methods, test and confidence intervals for the volatility persistence parameter, which are robust to weak instruments and dynamics. The proposed tests control levels and exhibit excellent power. We illustrate the empirical relevance of this proposed test using mixed frequency, stock price, and option data. The paper is available in my website, and I also have a paper in the poster session where I use higher order stochastic volatility model to forecast volatility. And so please look at that poster, and if you have any comments, please email that to me. Thank you.